In this lecture, we're going to describe formal charge. Formal charge is something that we use to assess the reasonability of a Lewis dot structure. It also helps us better understand resonance structures as well. It's kind of like our evaluative tool for what was the thing that we built with our electron dot symbols. So formal charge isn't real. It is just a bookkeeping method. It assigns each atom an imaginary charge, not real, in a Lewis structure. And it helps us distinguish between competing Lewis structures to see which would be the most likely to represent that molecule in nature. So, with that giant asterisk that this is all imaginary and literally just a pattern we can impose to help us better predict how things will look in nature, formal charge is equal to the number of valence electrons, and this is for each element or each atom in a molecule, minus the sum of its non-bonding electrons. So those are going to be lone pair electrons, plus half of its bonding electrons. So that's electrons in a bond. Okay, so we'll apply this in a second in the next slide, but talking about it a bit more. An atom's formal charge is going to indicate the charge it would have if all of the bonding electrons were shared equally between it and the bonded atom. So we won't take electronegativity into account here. And the sum of all the formal charges in a molecule will need to equal 0 if it doesn't have a charge. Now, if it's an ion, it'll be then equal to its ion charge. And so we'll assign a formal charge to each atom in our structure. And if it's a neutral molecule, all of those need to add up to 0. Let's look at this. All right, let's keep working with ozone since we just talked about it as a resonance structure. And let's evaluate the formal charge for each of its two resonance structures. And that's what we use this a lot for. We use it for kind of comparing to resonance structures. We also use it for comparing just like different Lewis structures of the same atom that see which one is the most likely. So let's go through this and let's do it for the first one, and then it'll be similar for the second. So for my first oxygen right here, the total number of valence electrons that oxygen has. So this is out of the context of the molecule, but oxygen has 6, right? So each of these are going to have 6. Now it's going to be minus the number of non-bonding electrons. Now this is where it'll change based on the atom. So the non-bonding electrons are these lone pairs right here. So I'm just going to highlight them. So for my first oxygen atom, the number of non-bonding electrons is 4. For my middle one, there's 2. And for my last one, there are 6. Now I'm going to subtract half the number of bonding electrons. And so I'm going to look at each of these bonds right here. So in between these so for the first one, it has just 2 bonds to that central oxygen, and there's 4 electrons there. So it's going to be minus half of those 4 bonding electrons, or 2. Now for my middle oxygen, it has 6 electrons that are part of a bond that are around it. So it's going to be minus 1/2 times 6, or 3. Now, looking at my last one, it only has 1 bond to it. So it'd be minus 1/2 of the 2 electrons that are in that bond. Okay, so for our first one, it's 6 minus 4 minus 1/2 of 4, which is 2. So it's going to have a formal charge of 0. Now, for the next one, I have 6 minus 2, so I'm at 4. Now, minus 1/2 of 6, which is 3. That's going to leave plus 1 left. For my last one, it's 6 minus 6. So I'm already at 0. Now minus 1/2 of 2 minus another 1. I'll be at negative 1. So my formal charges in this molecule are 0, plus 1, and minus 1. Notice that we made up that when we were building our Lewis structures, that rule that if it has its like preferentially oxygen with 6 valence electrons will always want to form 2 bonds. Well, this is definitely an example where we have oxygen forming 3 bonds and oxygen forming 1 bond. And so it's possible to do more than that. It'll want to be 2. And you notice the oxygen that has only 2 bonds and 2 lone pairs, it has the formal charge of 0. And the ones that break that kind of like rule, it's not really a rule, but break that expectation are the ones that have a formal charge associated with it. So in general, better structures are going to have fewer formal charges in general. They're going to have smaller formal charges, which means their magnitude is smaller. So like a +1 or a -1 is better than a +3 or a -3 formal charge. And the other trick to this is that the negative formal charge is on the more electronegative atom. Now, in this case, the electronegativities are all the same because it is the same element. But if I had a carbon and an oxygen, let's say, in some sort of larger molecule, it wouldn't make sense to have a formal charge of -1 on carbon and a +1 on oxygen at all. It would make more sense to have that -1 formal charge on the oxygen and the +1 on the carbon because my carbon has an electronegativity of 2.5 and my oxygen has 3.5. Because it has a higher electronegativity, it'll attract electrons better. It'll be more stable for the more electronegative atom to be able to have a slight negative or a formal negative charge on it. Let me put that up so you can see it. Okay, so let's actually do this other one now, and hopefully it'll be a little obvious since it's like the resonance structure. So again, all of these have 6 valence electrons, right? So I'm going to go down and assess these. So for my first one right here, I have 6 valence electrons. I have 6 electrons that are in lone pairs and are not bonding. And I have 2 that are participating in a bond. So I'll do 1/2 of 2. That's going to give me my -1 formal charge. For my central one, I have 6 valence electrons. I have 2 that are non-bonding that I'm subtracting. And then I'll subtract 1/2 of the 6 electrons that are participating in a bond. Another way that I learned this that I kind of prefer is I just subtract the number of bonds, right? 1/2 of the bonding number of electrons is the number of bonds, right? There's 3 bonds to that central oxygen. 1/2 of 6 bonding electrons equals 3. So for my next one, I have 6 valence electrons minus 4 of my electrons that aren't participating in a bond, and then minus 2 bonds. So let's see, I switched it to the other way. So I'll have a +1 for my central and a 0 for my one on the end. So this will have a -1 formal charge, +1, and a 0 formal charge.